So today my plan is to build up on what we started last time. Before we start, I would like from us to think about the project. I would like to build a two-dimensional idealization of the lower extremity, and we would like to look at vertical jumps. If you recall from last lectures, we built something like this. This is the first step in studying human motion analysis is idealization, which is representing an anatomical structure with the weightless segments and mass points. Does that make sense? And that's what we want to do first. And then we have in the literature, there are some publications that can tell you exactly if I'm, I don't know, 5'5", 5'6", how much would my arm weight and where should I place the mass point. Make sense? So we have in the literature some information about that. Now, if you recall from biomechanics, we said we can analyze a system. You can analyze the entire human body, or you can analyze components of the human body. What I would like to analyze is just the lower extremities from the hip down, 2 dimensions. So what we want to do is 1 segment, 2 segment, 3 segments. That's it. That's all we want to analyze. I want from you to do something called idealization. That's step 1, which is building the segments and mass points. And we will create something called the relation matrix from it. Now, step 2 is formulating the equations of motion that will describe the movement of this structure. Then we will solve the equations of motion to find the trajectories, the position and velocities and the accelerations. And then we can say that we have completed the analysis of the model, the human motion analysis. So think about it. Idealization, formulating the equations of motion, and then solving the equations of motion. And solving the equations of motion, we have 2 ways. We have something called the initial value problem, and we have something called the boundary value problem. And we're going to learn about how to do both of those. Step 1 is idealization. And this is supposed to be a deer. And here's the thing. Rule number 1, you need to have a starting point. You need to have a 0, 0 point. Make sense? That's rule number 1. Rule number 2, which is important. We cannot have closed loops. So when you build your model, we can't have this connected to this point. These 2 points. Does that make sense? If we do this, the model will fail. We're not going to work with our model. Then we need to formulate something called the relation matrix. Now, when you did statics and dynamics, we studied the kinematics of a rigid body, an isolated rigid body, like a ball, right? And we looked at the velocity and the acceleration. Now, this is a multi-segment coupled pendulum system. It means that it's all connected to each other. Now, one of the important aspects of it, how would I know where is mass number 3? If I didn't show you this structure, there should be a way for us to identify where mass 3 is and on what segment, and it's connected to which other segments. And do we have other masses on that segment? And that is the relation matrix. So our relation matrix gives us from its name, the relation. It shows you the connections and it shows you the mass points. Now, how many mass points do I have here? 1, 2, 3, 4, 5, 6 mass points, correct? How many segments? 1, 2, 3, 4, 5 segments, correct? Now, in your relation matrix, the number of rows is equal to the number of masses. So I will be having six rows. The number of columns equal to the number of segments. So my relation matrix will look like this. Look at that. Again, the relation matrix is another representation of the structure, but without looking at the structure itself. 6 masses, 1, 2, 3, 4, 5, 6 rows. 5 segments, 1, 2, 3, 4, 5 columns. How do we formulate this mass matrix? Here's the thing. I need to start from an origin, from the starting point, correct? Now, this starting point, how far on the first segment my first mass? Remember, those segments are weightless, correct? So they do not contribute to movement or acceleration. The only thing that contributes to movement acceleration is the mass. So first segment is L1, but my mass is away Z1 from the origin, and that's why I put Z1 here. Now, mass 2, I have to pass from all L1, then Z2 to reach mass 2, correct? That's why on the second row, I have the entire length of the first segment, and then Z2 of the mass point. Now, this is 3, correct? I have to go the entire L1, L2, and then Z3 to reach to that mass point. So L1, L2 is Z3. Now, if I want to go to, I have 2 mass points on the fourth segment. So I will go the entire L1. Do I have anything on L2? 0. Anything L3? 0. So it's connected immediately to L1, and then I have M41, which is Z41. Same thing for the next one, 0042, Z42. And the last one, M5, L1, L4. So I have 00 on the L1 and L2, entire L4, and then I have Z5. And that's our relation matrix. Now, if you have the relation matrix without the structure, you should be able to replicate the structure itself. You should be able to build it. And if I give you the structure, you should be able to construct your relation matrix. Remember, guys, we select a structure, we do idealization. We need to formulate the equations of motion, solve the equations of motion, and that is actually how we do motion analysis. Now, here's the thing. In our field in rehabilitation engineering, you have 2 aspects. One of them is developing the wheelchairs and robotics and all these assistive technologies, and the other part of it is human motion analysis. And the biggest difference between what you learn in statics and dynamics and here is that they were using one rigid body. Now we have connected segments with mass points. Idealization is looking at a structure and then saying, well, I want to simplify it. So I would like to put these segments and mass points in these locations. Now, formulating the equations of motions and solving it, that's a different story. But that's the first step in any human motion analysis. For example, that example there, I'm looking at the upper extremities. You're looking at the lower extremities. Someone might come to you and say, well, can you build a mathematical model for a horse, right, in 2 dimensions? So any biological system, if you want to study the motion of that system, the first step is idealization. Putting the system on drawing, but the relation matrix is another representation of how these things are connected. And then the formulation of the equations of motion, we will do something different about how we will build these. Second step is formulating the equations of motion. And we have 2 ways. And that's called modeling approach, for the dynamic modeling approach. So we have something called forward dynamics and something called inverse dynamics. In the forward dynamics, I'm giving you the forces and I'm asking to find the motion. In the inverse, I'm giving the motion and I'm trying to get the forces that created these motions. We are using Newton approach, which is based on the force. And there is another approach called the Lagrange approach. Lagrange is based on the work and the energy. If you are interested in this field, any movement, any motion or motor task, the first thing you need to do is to idealize it, look at the angles that you're interested in, build the equations of motion, solve the equations of motion, and then you can help people do whatever analysis. Now, Newton uses the forward and inverse dynamics. There are advantages and there are limitations of each one of those. The limitations of these 2, for example, in the forward dynamics, you need the forces, correct? Now, in the human body, assessing the forces in the joints is very complicated, right, to find the motion. Also, in the inverse dynamics, you need someone to perform the motor task to give you the forces that generated it. So these 2 ways cannot predict new motion, right, and cannot assess the net joint muscle forces. So these 2 things are important. let's say, remember when I talked about the example of the lady that she was playing in the tennis game. We found new motion for her to perform. We can't do this using this model. And we wanted to assess the forces in the joints. That's also complicated, difficult. That's why we created a new way, and that is what I worked on when I did my master's, called the boundary method with my advisor. So the boundary method is different from the forward and the inverse dynamics. It can solve for new motions, and also it can give you the net muscle joint forces. And that's the beauty of the boundary method, and why it's important to learn how to solve this. Keep in mind that the net muscle forces are output of the method, and that's why it's important. The problem with forward and inverse dynamics is we cannot predict new motions, and we cannot find the net joint muscle forces, the forces. Now, a quick look at what we did, right? This is an example, right? So I have a model. I did the idealization for the lower extremities. This is walking, right? That was a model of walking. Now, I selected 3 angles, 1, 2, 3, correct? And we had this configuration space. I don't like to look at this into configuration space. We built something called configuration. We built something called configuration space of the angles. You have 3 angles, correct? You can build the same thing with these 3 angles. And then your motion, step by step, each time, each green line will have a different angle. So your angle, which started here at the initial condition, you have 0, 90, and 0, correct? Your initial standing. That could be your point here. So 0 and 90 and 0, so that should be something here, right, on this point. And then as you move, this point will be moving depending on the 3 values. And that's what we call as the motion trajectory. And that's what we would like to solve for. You would like to see how the system is moving. Now, if you have this trajectory as theta, you can do the derivatives and you get the velocities, correct? Derive it again, you get the acceleration. So that's a kinematic analysis of the human motion structure. Does that make sense of how to do this? So this is all about step 1, which is doing the idealization and looking at the ranges of motion, maximum, minimum, and think how is that going to move? How is your angles will change on the motion trajectory? What's your trajectory? So instead of looking at theta 1, theta 2, theta 3, or x, y, and z, I am just tracking one trajectory in the configuration space, and that's what we're looking for. If I want to ask you this question, you have 3 angles in 2D. How many angles would there be on 3D? So you will have theta and phi. In each so we have x and y, you have 2 dimensions. You will have 1 angle to represent what's happening. So 2 minus 1. 3 dimensions, 3 minus 1 will be 2. So theta and phi, or phi, will be your angles for each one. So each segment will have 2 angles, so 6. So you'll have 6 equations of motion to look at. Does that make sense? And that is actually how we use mathematics, matrices, and the geometry in looking at human motion analysis. So I'm applying it to a real life challenge.